In this module, I want to talk to you guys about pressure and temperature and how this can actually affect the solubility of gases or solubility of solids as well. But we're gonna focus on solubility of gases, solubility of solids, and how that's affected by both of these. You also do need to know Henry's law and be able to calculate solubility of a gas in a solvent. First, let's talk about solutions in general. So we see on a graph here, we've got sodium nitrate, calcium chloride, lead nitrate, etc. We've got different salts here. Remember what a salt is? A salt is something whose anion is not hydroxide, cation is not hydronium ion, and these happen to be metal salts because the cation happens to be a metal. All of these do exist in solid form at regular room temperature, and what this chart is looking at is their solubility versus their temperature. So we see here temperature, this is in degrees C, we could convert that to Kelvin if we wanted to, and solubility specifically showing me how many grams of solute, this being our solutes, how many grams of solute will dissolve in 100 grams of water at the corresponding temperature. So first, the temperature effect on solubility. For solids, as we increase the temperature, most often the solubility will also increase, which is what we see on the charts here. We see all of the lines increasing as we increase the temperature, because temperature is increasing this way, except, sodium sulfate, we see an opposite effect here. But for most species, most often as we increase the temperature, the solubility of that solid will increase. More will get into in solution. Does that make sense? What do you guys think? I want you to think about, remember we talked about what happens, how do solutions form? For a solution to form, let's talk about KCl, potassium chloride. In order for potassium chloride to form a potassium chloride solution, we must break apart the ion-ion attraction between the potassium ions and the chloride ions. We must also break apart, in this case we're talking about water as our solvent, we must break apart the hydrogen bonds holding the water molecules together. The water molecules will then completely hydrate the potassium ions and the chloride ions, forming the solution. If I give the system more energy in the form of temperature, a higher temperature gives it more energy, gives it more movement, it's more likely to be able to dissolve more because we're adding heat to that system, allowing it to overcome those intermolecular forces holding the particles together, which is then going to allow that solution to form. What we do see, though, is for gases, an opposite effect. The solubility of your gas is going to decrease as we increase the temperature. And I want you to think about that for a minute as well and think, okay, well, why is that happening? If it increases with solids, why is it decreasing with gases? And then think about the behavior of gases. Going back to vapor pressure, we talked about vapor pressure already, we talked about gases and their behavior already as well. If I have a gas, so let's say I have a glass of some kind of carbonated beverage. Carbonated means I've got CO2 dissolved inside, CO2 gas. You pour this out in a glass, and if you pour it out straight out of a bottle, you can see the bubbles fizzing out at you. The faster I heat this up, the faster those bubbles will pop out, and your drink will go flat or lose its carbonation. Well, this is a gas, though. If I give it more energy, it's got more energy to completely escape from solution. It doesn't need to stay dissolved anymore. It has enough energy to completely escape all intermolecular forces and enter into the vapor phase. So whereas solids tend to be more soluble as I increase the temperature, gases will actually decrease their solubility with an increase in temperature. One important application of this is thermal pollution of lakes and streams. With thermal pollution, what's happening, thermal meaning heat, okay, so we're dumping water into these reservoirs and at a higher elevated temperature than normal. Well, what happens then is the dissolved gases in the water escape more easily. So things like oxygen that our aquatic life often is able to absorb straight from the water, there's less of it. So again, thermal pollution, meaning I kind of think about it as temperature, but it's heat. Thermal is heat. It's a heat pollution. We're dumping the water back in at a higher temperature. That higher temperature means there's less gases dissolved. If there's less gases dissolved, that means our aquatic life has less availability of those gases they need to survive, and then we end up with an increase in aquatic death, unfortunately. And it is a pollution because it's hurting our lakes and our streams. Let's delve into this graph a little bit more and answer some questions specifically concerning this graph. Looking at the graph, how many grams of sodium chloride are required to saturate 500 grams of water at 100 degrees C? Okay, well, I've got my degree C here. I see 100 degrees here. It says sodium chloride, so I find my line with sodium chloride. I've got it right here. I'm like, okay, cool. I look across. Inevitably, someone's going to say 40. 40 grams of solute. It's not correct, though. That is 40 grams in 100 mils of water. Assuming this is a linear relationship, and it looks very linear on this chart, the way that the sodium chloride line is increasing, assuming this is a linear relationship, we will need about 200 grams of sodium chloride to completely saturate 500 grams of water at 100 degrees C. Why? Well, at 100 degrees C, 100 grams of water needs 40 grams of sodium chloride. So if I'm going to multiply this by 5, I better multiply this by 5 as well. Sorry, I wrote these under the wrong. It should be this by 5. So if I want 500 grams of this, I'm going to need 200 grams of this if I'm staying at the same temperature. That should definitely, need to turn on a smaller eraser, say NaCl as well. What about this? If I have 30 grams of KCl and I dissolve this in 100 grams of water at 45 degrees C, how many additional grams of KCl would be needed to make a saturated solution at 80 degrees C? Okay, so at 45 degrees C, KCl, 45 degrees C, I can dissolve up to 40 grams. I've only dissolved 30 grams, which means I am not yet saturated. That means I need 10 grams more of KCl to be saturated at 45 degrees C. Then it says, okay, what would I need? How many additional grams do I need to make a saturated solution at 80 degrees C? Well, 80 degrees C to KCl is just above the 50 gram mark. I've added 30 grams. I need about 50 grams of KCl at 80 degrees C. I've added 30 grams of KCl. So I need about 20 grams of KCl to saturate this. 20 additional grams of KCl added to saturate this at 80 degrees C. How does this information factor into it? Or this information? It's useless. It's erroneous information to throw you guys off, to be completely honest. Other than the fact that I need to put this piece of information into here. But this whole at 45 degrees C thing doesn't matter. You can tell me it's not saturated right now, but I don't care about the 45 degrees C. I care about the 80. Don't let additional information in the question throw you off too much. I need the 30 grams in the sense that I need to know how much more to add, but I don't care that it's 30 grams at 45 degrees C. I just care that I've already added 30 grams. How much do I need to reach a saturation point at 80 degrees C? If 50 grams of water was saturated with potassium chlorate at 23 degrees C and it slowly evaporated to dryness, and the rest of the question got deleted, I apologize for that. Let me write that out quick. How many grams of the dry salt will be recovered? So potassium chlorate, hopefully you remember which one potassium chlorate is. If you get confused, hopefully you can at least start to narrow it down. Students have a hard time with chlorate. Remember, at least you can remember potassium, so you should be able to narrow it down to at least one of these two. Hopefully you remember this is dichromate. This is chlorate. So I've got 50 grams of water, and it's saturated at 23 degrees C. So I'm about right here. Let's say that's about 8 grams of KClO3 per 100 grams of water. But the question tells me I have 50 grams. That means this has been divided by 2, which means this is also divided by 2. So I will recover about 4 grams of KClO3 if I have 50 grams of water completely saturated with potassium chlorate at 23 degrees C, and I slowly let it evaporate to dryness. And D, a solution contains 36 grams of sodium chloride in 100 grams of water at 90 degrees C. Is the solution saturated? 36, a little bit above here. Go across at 100 or at 90 degrees C. No. And I made that. We can even zoom in. We can see that that is definitely above the 36 gram mark. So no, we're close to getting to the saturation point, but we are not there yet. We need to add maybe another 3 or so grams of sodium chloride, 3.5 maybe, to reach the saturation point. What about the effect of pressure on solubility? The solubility of solids and solids into liquids is not greatly affected by the pressure. It doesn't really have a large overall deviation. It's not going to do much. You can increase the pressure and it's just going to look at your temperature is the real effect on solids. But gases will be affected by pressure. Gases in liquids is directly proportional to the partial pressure of that gas over the liquid. Remember how to calculate partial pressure? P sub A equals X sub A times P total, where X sub A is your mole fraction. You guys should be able to calculate that. And you can actually calculate the solubility of a gas using Henry's law. We see here that the solubility of a gas is equal to K sub H, which is Henry's law constant for the gas or liquid mixture. Those are constants you can look up, times the partial pressure of the gas. I'm not going to do an example like that, but you should be able to do that if I gave you K sub H. If I told you the total pressure of the system and told you the components of the system, you should be able to calculate the mole fraction. With that, you should be able to calculate the partial pressure of that gas and then plug and chug Henry's law equation. We do see, again, the solubility of these gases is going to, as we increase the pressure, more of the gas will dissolve. As I decrease the pressure, less gas dissolves. If I have a closed system and I increase that pressure, where's the gas particles going to go? They're going to go into the solution to reestablish an equilibrium. You will learn more about equilibrium in very, very soon. Actually, in just give it a chapter or two, you're going to learn equilibrium, and it's this rate of how much do they go back and forth. But if I increase that pressure, more gas will dissolve. You can calculate how much with Henry's law. And again, I'm not going to calculate it for you, but you should know how to do mole fractions. And you should remember this equation. The partial pressure is equal to the mole fraction times the total pressure of the system. Two important applications of this would be the bends and a hyperbaric chamber. The bends is what we have when you go scuba diving. It's also known as your decompression sickness. This happens when a scuba diver is pulled up too quickly from the water. When scuba divers go down real low in the water, they're under a different amount of pressure than we have at regular atmosphere for humans. And so the diver's breath is compressed air that contains a lot of nitrogen at that point. At high pressure under the water, the nitrogen gas goes into the body's tissues. And this doesn't cause a problem for the diver when they're down in the water because their body's equilibrated to be under that pressure. As the diver rises to the surface, if we bring them up at a slow enough rate, the nitrogen gas can slowly move back out of the tissues and safely leave the body through the lungs. No problem. But if a diver is raised too quickly or rises to the surface too quickly themselves, the nitrogen is going to actually form bubbles in the body that can cause tissue and nerve damage. In worst cases, it can cause paralysis or death. So personally, I've only never seen it talked about like in movies and stuff or TV shows, but they're like, you can't, if you have someone that's scuba diving, you can't bring them up. If God forbid there's an accident, you can't bring them up too quickly because you can cause more damage by bringing them up too quickly. And it's kind of a risk-benefit analysis there. And hyperbaric chambers. A hyperbaric chamber works by reduces swelling while flooding your tissues with oxygen. So it has an elevated pressure in the chamber itself, increasing the amount of oxygen in your blood. And the whole point of a hyperbaric chamber is to break the cycle of swelling, keep your muscles from starving for oxygen, and keep the oxygen traveling through your tissues. So it puts you under a large pressure system with a lot of oxygen, which is going to get that oxygen into your tissue, into the tissue within your body faster.